May 19, 1997. A small team of scientists from the National Oceanic and Atmospheric Administration, working on an autonomous hydrophone network in the equatorial Pacific Ocean, was conducting a routine monitoring session. Nobody expected anything unusual. They were listening for underwater earthquakes, standard procedure, a Tuesday morning. Then something came through the speakers that stopped everyone in the room. A sound rising in frequency. Fast. Powerful. Unlike anything in their reference database. Dr. Christopher Fox, the chief scientist of the National Oceanic and Atmospheric Administration's Hydroacoustic Monitoring Program, described his first reaction in a single sentence. In 30 years of ocean research, I have never heard anything like it. The sound lasted approximately 1 minute. It was loud enough to be simultaneously detected by hydrophones, underwater microphones, separated by nearly 5,000 kilometers. To be detected at that distance, at that volume, the source had to possess extraordinary power, more powerful than any known biological or geological event recorded up to that point. The team immediately gave it a name, unofficially, based on the shape of the waveform on their screens. They called it the Bloop, and then they asked the only honest question they had. What on this planet could have made that sound? To understand why this sound was so alarming, you first need to understand something about the ocean that most people never learn. The ocean is not silent. It is one of the most acoustically active environments on Earth. At a certain depth, somewhere between 600 and 900 meters, something extraordinary happens to sound. Temperature and pressure reach a point of equilibrium. At this depth, sound does not scatter in all directions the way it does in air. Instead, it bends. It curves. It becomes trapped in an invisible horizontal layer. Scientists call this the sound fixing and ranging channel. The man who discovered it was a military physicist named Morris Ewing. In 1944, during World War II, Ewing was working for the United States Navy on a simple problem. If a pilot was shot down over the ocean, how could rescuers find him before he drowned? Ewing hypothesized that if the pilot dropped a small explosive charge before hitting the water, the sound would travel through this deep channel and be detected thousands of kilometers away. He tested it. It worked. This proved that the ocean could carry sound across entire ocean basins with virtually no loss of energy. Strange sounds were simply ordinary geological or biological events, amplified far beyond what seemed physically possible. It was a clean explanation. It held for decades. But the Bloop did not fit into it cleanly. Even accounting for the channel's amplifying effect, the source was still calculated as significantly more powerful than any known geological event of that era. The channel was not an explanation, it was only an intermediary. When the National Oceanic and Atmospheric Administration published the Bloop data in 1997, the scientific community did not panic. It began an investigation. The team proceeded with a systematic comparison. They compared the Bloop against every known sound in their marine acoustic database: underwater earthquakes, underwater volcanoes, ship propellers, known whale species, military sonar systems. Nothing matched. The first serious scientific theory came from geophysicist Robert Giac of the National Oceanic and Atmospheric Administration's Pacific Marine Environmental Laboratory. Giac proposed that the Bloop matched an icequake. An icequake is the sound produced when massive sections of Antarctic ice crack, when ice shelves fracture under their own pressure and collapse into the ocean. The evidence was compelling. The Bloop's point of origin was triangulated to an area near Antarctica. The frequency profile fell within the range of large-scale ice fracture events. By 2012, The National Oceanic and Atmospheric Administration's official position was that the bloop was most likely an ice quake. The case seemed closed, but Jack himself noted something that most news reports ignored. The 1997 bloop was still significantly louder than any glacial earthquake recorded since. Not slightly louder, significantly. And since 1997, despite more hydrophones, better equipment, and continuous monitoring, nothing like it has been recorded again. The question the data actually raises is not whether the bloop was an ice quake. The question is, what kind of ice quake was it? And why has nothing similar occurred in 27 years of continuous monitoring? The bloop was not the only anomaly in the archive. Between 1991 and 1999, the monitoring network recorded 4 other sounds that remain only partially explained. Julia, March 1st, 1999. 15 seconds. Detected across the entire Pacific Basin. Hypothesis: a grounded iceberg near Antarctica. The iceberg was never identified. Train, 1997. Its waveform looks exactly like railway wheels on a spectrogram. Hypothesis: seafloor volcanic activity near Antarctica. The source was never located. Upsweep, August 1991. Not a single event, seasonal. Louder every spring and autumn. Quieter every summer and winter. Hypothesis: an active underwater volcanic site in the southern Pacific. That site has never been visited. Slowdown, May 19th, 1997. The same day as the bloop, same ocean. But where the bloop's frequency rose, the slowdowns declined. Over 7 minutes, 2 sounds, same day, same region. Nobody has formally analyzed whether they're connected. Every sound has a partial explanation. None has a complete one. And every single one points to the same place, the waters around Antarctica. Here is something most people don't know. As of 2024, approximately 73% of the ocean floor has never been mapped to modern resolution. We have more detailed maps of Mars than of our own ocean floor. That is not a metaphor. That is a measurement. The triangulation coordinates for the bloop were calculated using 1997 maps. Maps covering perhaps 5% of the resolution needed for true precision. Sound in the deep channel doesn't travel in straight lines. It bends. It reflects off terrain. If that terrain is unknown, the origin point moves. Jack acknowledged this directly. The coordinates were an estimate, a good one, but built on incomplete data. In 2024, a research team mapping a previously unexplored section of the southern Pacific discovered an entire underwater mountain range, thousands of meters tall, that wasn't in any database. This happens regularly, which means every acoustic model we've built, every origin point we've calculated, was built on a map with pieces missing. Here's what the data actually tells us. In 1997, the National Oceanic and Atmospheric Administration, the United States federal agency responsible for monitoring the world's oceans and atmosphere, recorded a sound of extraordinary power near Antarctica. The most credible explanation, a large-scale ice quake, fits the evidence. But it doesn't account for the full magnitude. And in 27 years of continuous monitoring, nothing like it has occurred again. 4 other anomalous sounds. Same region. Each partially explained. None completely. All analyzed using maps covering less than 30% of the actual terrain. Dr. Robert Giac, the scientist who has spent more time on these sounds than perhaps anyone alive, wrote something in 2021 that stayed with me. He said, "Every year of new recordings shifts the baseline. What seemed anomalous in 1997 sometimes looks less anomalous with 2021 data. What seemed explained in 2005 sometimes looks less explained when you map the terrain the sound passed through. The bloop was probably an ice quake, but probably is not, certainly. And in science, that distance between probably and certainly, that is where the next 30 years of research live. The ocean is still transmitting. We are still learning to listen.